సో డియర్ స్టూడెంట్స్, ఇప్పటి వరకు మనకు తెలిసినటువంటి సిద్ధాంతాల ప్రకారం ఫర్ ఎగ్జాంపుల్ ఆక్సిజన్ కనుక మనం తీసుకున్నట్లయితే ఆక్సిజన్ మనకి వ్యాలెన్సీ బాండ్ థియరీ ప్రకారం గమనించినట్లయితే ఇట్ షోస్ డయామాగ్నెటిక్ క్యారెక్టర్, బట్ ఎక్స్పెరిమెంటల్లీ ఇట్ ఈస్ ప్రూవ్డ్ దట్ oxygen is paramagnetic. In addition to that, previous theories unable to explain the molecular ions, existence of molecular ions, existence of O2 plus, existence of O2 minus, existence of O2 2 minus. So for such type of ions also there is no correct clarification. So to explain the magnetic characters, to explain the existence of ions of polyatomic species, molecular oxygen, molecular ions. Now we have one more important theory in chemical bonding. Today let us move to that concept which is called as molecular orbital theory. So if you observe molecular orbital and atomic orbital, the difference between atomic orbital and molecular orbital is, in atomic orbital electron belongs to orbitals of atoms, but in the case of molecular orbital electrons belongs to molecular orbitals present in the molecule. So these molecular orbitals are obtained by different methods. Among those, the first method is 𝗧𝗦𝗔𝗧 method, linear combination of atomic orbitals. So according to 𝗧𝗦𝗔𝗧 model, or according to 𝗧𝗦𝗔𝗧 method, linear combination of atomic orbitals, let us consider hydrogen molecule which contains 1s orbital. So this is called as atomic orbital of one hydrogen atom. This is 1s orbital of another hydrogen atom. So these two atomic orbitals combine together and produces two set of molecular orbitals. Among those, one is obtained by constructive interference or electron waves in phase. Second one is obtained by destructive interference, electrons out of phase, and this is called as bonding molecular orbital, and this is called anti-bonding molecular orbital. If you observe this bonding molecular orbital, this is atomic orbital energy, and now this is molecular orbital energy. So from bottom to top, this is order of increasing energy. That means this bonding molecular orbital has lower energy than that of the atomic orbital, whereas this anti-bonding molecular orbital has higher energy than the individual atomic orbitals. So just now I told, in the linear combination of atomic orbitals, if two atomic orbitals combine together, then we are getting two molecular orbitals. One is obtained by constructive interference, another one is obtained by destructive interference, additive effect, subtractive effect, electron waves in phase, electron waves out of phase. So whenever two atomic orbitals produces two molecular orbitals, one is called bonding molecular orbital having lower energy than that of atomic orbitals. Another one is called as anti-bonding orbital which has higher energy than that of atomic orbitals. Now if you observe these 𝗧𝗦𝗔𝗧 combination, linear combination of atomic orbitals, now I am taking SS combination. So this leads to plus over plus leads to constructive interference. Then if these two atomic orbitals combine together and produces one molecular orbital, because this is obtained through constructive interference, this is called as bonding orbital. Now if you observe plus over minus, this is called as destructive interference or electron waves out of phase leads to anti-bonding orbital. This is anti-bonding molecular orbital. In this anti-bonding molecular orbital between nuclei, this is some type of repulsive. That means the electron cloud away from the nucleus, electron cloud away from the nucleus, and in between these two centers there is no electron density, called as no. So if these two atomic orbitals leads to bonding orbital and these two atomic orbital leads to anti-bonding orbital, because we are taking s and s orbital overlap, s and s combination always gives a sigma bond. That is why this is called sigma 1s orbital. Now if you take ss combination here, this is also sigma bond, but this is anti-bonding molecular orbital. These anti-bonding molecular orbitals we are representing with a star. So sigma is bonding molecular orbital and sigma star is anti-bonding molecular orbital. So SS combination leads to sigma SS combination leads to sigma SS bonding orbital and sigma SS anti-bonding orbital. Now if you observe the combination of p orbitals, So this is one p orbital, another p orbital. So this combination plus over plus, this is also constructive interference, leads to bonding molecular orbital, and this is the shape of the bonding molecular orbital obtained by constructive interference of two orbitals. Now, and if you observe this type of combination, this is nothing but destructive interference plus over minus leads to antibonding molecular orbital, and this is not where the electron density is less in between centers of these two orbitals. Now, we are talking about linear combination of p and p orbitals. So, pp leads to sigma bond as well as pi bond. So, this is sigma and this is sigma star, linear overlapping. Now, let us move to same pp orbitals, but if total 3 p orbitals are there, among those 3 p orbitals, one p orbital forms sigma bond, remaining 2 form pi bonds. So, for differentiating that, in the previous case, we observed the linear combination, now linear over now parallel overlapping. That means plus over plus, minus over minus leads to one molecular orbital, constructive interference. Now, this is pi bonding orbital, pi bonding molecular orbital. This is the nodal plane where the electron density is 0 between these two. Now, plus over minus, minus over plus, this is away from the nucleus, away from the nucleus, away from the nucleus, away from the nucleus, here and here, no electron density, so called as nodal plane. So, this pi molecular orbital has one nodal plane, whereas pi star molecular orbital has two nodal plane. That means, if you observe, the combination of S and S always gives rise to sigma bonds, whereas combination of p and p gives sigma bond as well as pi bonds. Now, after observing all these types of combinations, they arrange all these orbitals in the increasing order of their orbitals, like 𝗹𝗶 principle. So, the rules we are following for atomic orbitals, అంటే మన atomic orbitals కి 𝗹𝗶 rule మనం ఫాలో అవుతుంటాము, Hund's rule ఫాలో అవుతుంటాము. అదే విధమైనటువంటి రూల్స్ we have to apply for molecular orbitals also. So, this is the increasing energy order, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2py, pi 2pz, sigma 2pz, 2px. So, that means if you observe here, I consider x axis as molecular axis. If x axis as molecular axis, this 2px forms sigma bond, 2py and 2pz form pi bonds. Now, if you pull here, this is one molecular orbital and each atomic orbital occupies 2 electrons. Similarly, each molecular orbital also occupies 2 electrons. That means here 2 electrons, 2, 4, 6, 8. Now, if you observe these two, they are present in the same line. That means these two are called orbitals of same energy. We call them as degenerate orbitals. So, whenever degenerate orbitals are available, we have to follow Hund's rule. That means 2, 4, 6, 8, 9, 10, 11, 12. Then 2 electrons here, 14 electrons. That means this is a configuration applicable up to nitrogen. Now, after nitrogen, that is from oxygen onwards, you have to follow this configuration. So, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2px. If you observe sigma 2px here, up to nitrogen, if you observe the homodiatomic molecules up to nitrogen, sigma 2px has more energy than the pi 2py and pi 2pz, whereas here after nitrogen configuration, that means from oxygen onwards, the sigma 2px has less energy than pi 2py and pi 2pz. This is the only variation. That's why I mentioned here 2 types of electronic configuration. That means if you observe homodiatomic molecules, 2 types of configurations we have to practice up to nitrogen and after nitrogen. Now, this is also called as 14 or less than 14 electron system, and this is called as, or this order we have to follow the species having more than 14 electrons. So, after observing these different types of molecular orbitals, this is a distribution of molecular, diagrammatically I am representing here 1s, 1s, these are all called atomic orbitals, these are also atomic orbitals. Combination of these 2 atomic orbitals leads to molecular orbitals, sigma 1s, sigma star 1s, bonding, antibonding, bonding, antibonding. So, bonding, antibonding, antibonding, antibonding. So, in this MOT, molecular orbital theory energy level diagram, sigma 2px has less energy than these two. Now here sigma 2px has more energy than these two. That is the difference compulsory you have to practice regarding the molecular orbital theory. Now based on this MOT, now let us move to one more important parameter introduced here called as bond order. So this bond order indicates number of electrons occupying bonding orbitals minus number of electrons in antibonding orbitals by 2. So we have to follow this formula for calculating bond order. Now I am taking one example here. Now I am writing O2. O2 means 16 electron system. Then according to molecular orbital theory, its configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So for oxygen, that is more than 14 electron system, what type of configuration we have to follow? This is 2, 4, 6, 8, 9, 10, 11, 12, 14. This is 14 or less than 14 electron system. This is more than 14 electron system. That means this configuration we have to write. So 1s, sigma star 1s, sigma 2s, sigma star 2s, next sigma 2px. So here I am writing sigma 2px2. Now these two are degenerate orbitals. That's why pi 2py, next we have pi 2pz, 1 electron, next pairing takes place. So overall 2 electrons. Next, so 2, 4, 6, 8, 10, 12, 14, 2 more electrons are there. Next we have to move to pi star 2py and pi star 2pz. So pi star 2py, next pi star 2pz, 1 electron. Don't write 2 electrons here because degenerate orbitals we have to follow Hund's rule. That means if you observe this oxygen electronic configuration, except this remaining all are paired electrons. That means now by using this formula, now I am calculating bond order. So bond order is equal to half of number of electrons occupying bonding orbitals 2, 4, 6, 8, 10 minus 2, 4, 5, 6, that is 2.0. So bond order of oxygen is 2. What we observed in the previous classes also, in oxygen molecule, between oxygen and oxygen we have double bond character. That is also supported by bond order 2. But the important advantage related to molecular orbital theory is because of the availability of unpaired electrons here, this oxygen is considered as a paramagnetic species. Now after writing oxygen electronic configuration, now I am going to O2 plus ion, existence of molecular ion. So O2 plus means we have to remove one electron from outermost. So that means we have to remove electron from bonding or anti-bonding, that is we have to remove electron from anti-bonding orbitals. That's why this bond order for O2 plus becomes half of bonding electrons 10 minus 5. This becomes 2.5. Now I am going to O2 minus ion. O2 minus ion means we have to add one electron to O2. So 1 electron is available here. We can accommodate one more electron here. Therefore, for this O2 minus ion, bond order is equal to half of 10 minus. In anti-bonding, we have to add electron. Previously 10 minus 6. In the case of O2 plus, it becomes 10 minus 5. We have to remove electron from anti-bonding. But here we have to add electron into anti-bonding. That means 10 minus 7 by 2, it becomes 1.5. Now I am going to O2 2 minus ion. That means we have to add one more electron into anti-bonding orbital. That means bond order becomes half of 10 minus 8 by 2, then it becomes 1. So bond order 2 here, bond order 2.5 here, bond order 1.5, bond order 1. So definitely these species exist. In some cases we are getting bond order 0 also. In such cases we can say that such type of species are unstable or does not exist. So from this bond order we can predict so many points related to these 4: O2, O2 plus, O2 minus and O2 2 minus. These two are very well known ions. This is called superoxide ion and this is called peroxide ion. But mainly this molecular orbital theory explains about the existence of these molecular ions. Now, after observing this bond order, actually bond order indirectly explains about number of bonds. So, if bond order is more, it indicates that between two atoms, if we have more number of bonds, definitely bond length decreases. That means bond length and bond order, these two are inversely proportional. If bond order is more, definitely bond dissociation energy more. If bond dissociation energy is more, definitely that species is stable species. That means if you observe these four molecules, which one has highest bond order means O2 plus. That means here I am writing first O2 plus, next O2 bond order 2, next O2 minus, next O2 2 minus. So, here O2 plus bond order is 2.5, O2 bond order 2, O2 minus bond order 1.5, O2 2 minus bond order is 1. So, this is the decreasing order of bond order. If this is the decreasing order of bond order, then we can say this is the increasing order of oxygen-oxygen bond length. Because this is decrease in the bond order, definitely this is also decrease in the decreasing order of bond energies. Because this is decreasing order of bond order, this is also indicating decreasing order of stability. That means stability is proportional to bond energy, proportional to bond order, inversely proportional to bond length. Very important relation you have to practice in competitive examinations, because they are giving 3-4 ions, they are asking arrange them in the correct order of bond length or bond dissociation energies or bond orders, or in terms of stability is also they are asking. But overall this bond order gives us very important information related to stabilities of the species. If bond order is positive value, exist. If bond order is negative or bond order is 0, such type of species unstable or does not exist. Now, let us move to a few examples related to this molecular orbital theory. Now, let us move to different examples related to molecular orbital theory. Let us begin with formation of hydrogen molecule. 2 electrons are available, then its electronic configuration is 𝜎1s2. For this, bond order is equal to 2 minus 0 by 2, that is 1. Next I am writing here He2, 4 electrons are there, its MOT configuration is 𝜎1s2, 𝜎*1s2, that means bond order is equal to 2 minus 2 by 2, that is 0. That means this type of species does not exist. Now I am going to He2 plus ion, 3 electron system, then its configuration becomes 𝜎1s2, 𝜎*1s1. For this, bond order is equal to 2 bonding electrons minus 1 antibonding electrons by 2, that is 0.5. That means this bond order 0 indicates that helium-2 does not exist, whereas we have molecular helium like molecular ion like He2 plus ions also. So, this is one advantage in MOT theory, in molecular orbital theory, for predicting the existence of molecular ions. Now, let us move to one more example, that is formation of Li2 according to molecular orbital theory. Hydrogen, helium, lithium, 3 electrons are there, that means total 6 electrons are available. Then its configuration is 𝜎1s2, 𝜎*1s2, 𝜎2s2. For this Li2, bond order is equal to 4 minus 2 by 2. That means bond order becomes 1. Now, if you observe Li2 plus ion, then bond order is equal to, that means we have to remove electron from bonding orbital, then this 3 minus 2 by 2 becomes 3 minus 2 by 2, it is 0.5. Now I am going to Li2 minus ion. Li2 minus means we have to add one more electron, but we have to add one more electron to anti-bonding orbital, then bond order becomes 4 minus 3 by 2, that is 0.5. So, now some confusion in these two ions. Just now I concluded that if bond order is more, bond length is less, but stability is more, bond dissociation energy is more. But in the case of Li2 plus and Li2 minus, both species have same bond order. If both species have same bond order, then among these two, which one is more stable? Suppose if they ask arrange these three, Li2, Li2 plus and Li2 minus in the correct order of stability. Then if we have same bond order, then please concentrate on the number of electrons present in the antibonding orbital. Here we have in Li plus 2, 2 electrons in the antibonding orbital, but here we have 3 electrons in antibonding orbital. That is why relatively when compared to Li2 minus, Li2 plus has less number of electrons in antibonding, that leads to more stable species among these two. That is why if you compare Li2, Li2 plus and Li2 minus, what the correct order of stability means? This one has highest bond order, so more stable. Next one is Li2 plus, next one is Li2 minus. That means if species have same bond order, then compare their stabilities by using number of electrons present in the antibonding molecular orbital. Now, in this molecular orbital theory, suppose if we have isoelectronic species, all isoelectronic species have same bond order, that means A and B are isoelectronic, then for those two definitely bond order is same. But if we have X and Y having same bond order, then those two need not be isoelectronic. So, all isoelectronic species have same bond order. If two species have same bond order, then those two species need not be isoelectronic. Just now in the previous example we observed that in Li2 plus and Li2 minus ion we got same bond order 0.5, but these two are not isoelectronic. So, this statement a very important statement, isoelectronic species have same bond order. If two species have same bond order, then those two species need not be isoelectronic. Now, let us move to some more points in this molecular orbital theory. Let us move to formation of C2 according to molecular orbital theory. C2, 12 electrons we have. Then according to molecular orbital theory, the configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, next pi 2py, pi 2pz. This is less than 14 electron system. For less than 14 electron system, sigma 2px has more energy than pi 2py and pi 2pz. Then this is the order of energy. Now we have to fill 12 electrons, 2 electrons here, 2 electrons here, 2 electrons here, means 8 electrons are over, 9, 10, 11 and 12. So, 2 electrons. So, this is bonding and anti-bonding. Actually, bonding means stabilization, this is destabilization. So, both are cancel out, stabilization, destabilization cancel out. But if you observe here, 2 electrons in pi 2py orbital, 2 electrons in pi 2pz orbital. So, this leads to one bond, this leads to another bond. But overall, if you observe C2 molecule, it contains 2 bonds. But the important point is both shows dash character, pi character. So, it is a very unusual representation this C2, because previously we observed that sigma bond exists independently, but pi bond exists only after formation of sigma bonds. But this is all are cancel out, stabilization, destabilization, but here one pi bond is available, another pi bond. That means if you observe bond order calculation also, it clears that in C2 molecule bond order is equal to 2, 4, 6, 8, 8 bonding electrons and 4 anti-bonding electrons. Then bond order 2 we are getting. Bond order 2 means two bonds, but here in the case of C2 both are pi character, both are pi bonds. That point also very exceptional behavior shown by C2 molecule. So, ఈ విధంగా మనం ఈ కెమికల్ బాండింగ్లో ఉన్నటువంటి వివిధ రకాలైనటువంటి బంధాలను తెలుసుకున్న తర్వాత ఇప్పుడు let us move to final conclusion related to chemical bonding chapter by observing different types of bond parameters. Totally we have 4 types of bond parameters. One is bond length, bond energy, bond angle and bond order. Now let us move to one by one all these bond parameters. The first one is bond length. This bond length indicates the distance between the bonded atoms. So I am taking two atoms here, A and B. Both are bonded with the help of covalent bonds. Now here, center of the nucleus of bonded atom A, center of the nucleus of bonded atom B. This distance from here to here is called as internuclear distance. Now this internuclear distance, because both have different sizes, and here this is called covalent radius of A and this is called covalent radius of B. Now if you observe this second diagram here, two molecules I am taking, these values related to chlorine. This is one is chlorine molecule, another one is chlorine molecule. So two chlorine molecules without bond formation are attracted to each other. Those attractive forces operating between these two molecules without bond formation are called as van der Waals force of attractions. So now we have two Cl2 molecule under the influence of van der Waals force of attractions. Now this is internuclear distance, and from here to here is half of the internuclear distance. That half of the internuclear distance is called as covalent radius. So internuclear distance is 198, half of this is 99 picometers. That means this 99 picometers is now considered as covalent radius of chlorine. Now between these two van der Waals forces are operating, and this is the distance you have to maintain for having this van der Waals force of attractions. Now half of this 360 by 2 180 picometers now called as van der Waals radius. So this is a covalent bonded molecule Cl bond, that is why this is covalent radius, and Cl2 molecule, another Cl2 molecule with the help of van der Waals force of attractions, that is why half of this distance is called as van der Waals radius. For a particular element, definitely always van der Waals radius is more than covalent radius. Now let us move to some important conclusions related to this bond length. So regarding this bond length, the first point is effect of resonance in bond length. Effect of resonance in bond length means, if you observe ozone molecule, this is one Lewis structure of ozone molecule. Another Lewis structure of ozone molecule, a different structure. These two are called resonance structures. If we have resonance, if you consider this structure, double bond is available, here single bond, and here double bond, then this is called resonance hybrid. Now if you observe individually this particular molecule, double bond length and single bond length definitely different, but in the case of ozone, both bonds are equivalent. Both bonds are equal in length. That means we have two bonds here in ozone molecule. If you observe only one structure, clearly we are observing double bond and single bond, different bond length, but experimentally in ozone molecule, both bonds are equal in length. That too, this bond length value is always intermediate between double bond as well as single bond. That means in ozone molecule, oxygen bond length is less than single bond length and more than double bond length. Like that, definitely this resonance influence bond length. Next one is, I am taking two carbon atoms, carbon single bond, carbon double bond, and carbon triple bond. So if you have carbon single bond, double bond and triple bond, that means as number of bonds between two specific atoms increases, definitely bond length value decreases. This value is nearly 1.54 angstroms, this is 1.34 angstroms, and this is 1.2 angstroms. So the second conclusion is, as number of bonds between two atoms increases, bond length value decreases. The previous one is resonance effect, now number of bonds between two atoms. Now let us move to third conclusion. In a group of similar compounds, suppose I am writing here HF, HCl, HBr, HI. In a group of similar compounds, definitely top to bottom bond length value increases due to increase in the size of halogen atom. So, HF to HCl, HCl to HBr, HBr to HI, bond length value increases. That means, in a group of similar compounds, top to bottom bond length value increases. This is third point related to bond length. Now, after observing this first bond parameter, that is bond length, now let us move to the second bond parameter, that is bond energy. Bond energy means the amount of energy required to break a bond in a molecule. So, this bond energy also influenced by various factors. Number one I am giving here, carbon, single bond carbon, double bond carbon, triple bond carbon. That means, as number of bonds between two atoms increases, definitely for breaking these bonds we required more energy. That means, the correct order of bond energy is CC single bond less than C double bond C less than C triple bond C. Here do not get confusion here, pi bond is weaker than sigma bond, but you are talking about breaking of double bond, not pi bonds. That is why total bond energy we have to compare. So, as number of bonds between two atoms increases, bond length decreases and bond strength or bond energy increases. And second point is, in a group of similar compounds HF, HCl, HBr, HI, down the group as bond length increases, definitely the bond energy decreases. That means, HF to HI, the bond dissociation energies decreases. Now, let us move to one more point related to bond energy. Here I am writing C bond C, here N bond N, here O bond O, and here F bond F. Now, I am comparing the single bond energies among these four elements, CC single bond, NN single bond, OO single bond and FF single bond. In the case of carbon, no lone pair of electrons, but in the case of nitrogen, one lone pair is available. In the case of oxygen, two lone pairs are available. Here we have three lone pairs. So, as number of lone pairs present on two bonded atoms increases, definitely the repulsions between the lone pairs increases. If repulsions increases, for minimizing the repulsions, definitely these two atoms moves apart and thereby bond becomes weak. That means, among these four, what is the correct order of bond energy means CC is greater than, NN is greater than, and this is greater. That is why carbon has a high catenation capacity due to strong CC sigma bond. Now, let us move to another point related to this bond energy. Here I am writing one word, homolytic cleavage. This is heterolytic cleavage, homolytic cleavage, heterolytic cleavage. That means, if we have a bond like XY, just one bond I am taking for explanation purpose. Two electrons are available here. Here also two electrons are available here. Suppose I am breaking the bond like this. Suppose I am breaking the bond like this. Then we are getting X with electron, Y with electron. But here we are getting X plus Y with extra electron. That means, these are called free radicals, these are called ions. So, this type of cleavage also we can differentiate by observing their bond energy values. That means, I am giving a statement here, the energy required for homolytic cleavage of the bond and the energy required for the heterolytic cleavage of the bond, if you compare, in which case we required less energy means energy required for homolytic cleavage is less than the energy required for heterolytic cleavage of the bonds. A very important conclusion, this type of cleavages we are observing in organic compounds. Now let us move to one more parameter, bond angle. So this bond angle indicates the angle between bonded orbitals. This bond angle, now I am giving some important conclusions. The first one is CH4 NH3 H2O, tetrahedral without lone pair, pyramidal with one lone pair, bent with two lone pairs. And that means if you have one lone pair and two lone pairs, definitely the influence of lone pairs on bond angles. Here we have bond pair repulsions, here we have lone pair and bond pair, here we have lone pair bond pair and bond pair repulsions. According to VACPR theory, lone pair repulsions are more than lone pair bond pair repulsions. Therefore, if you compare CH4, NH3 and H2O, the bond angle gradually decreases. Here we have 109 degrees, here we have 107, here we have 104. That means as number of lone pairs near central atom increases, the bond angles decreases. If other factors if we ignore, only we are considering here the repulsions among electron pairs. That is first point related to bond angle. Now let us move to the second point. Now I am taking here H2O molecule and OF2 molecule. Here both have same central atom, oxygen. Near central atom we have same number of lone pairs. Now we are comparing these two bond angles. Here in H2O molecule, electronegativity of central atom is more than surrounding atom. But here electronegativity of surrounding atom is more than central atom. If electronegativity of central atom is more than surrounding atom, definitely bond pairs of electrons move towards oxygen. Here away from the central atom. If bond pairs are very close to each other, in the case of H2O molecule, definitely even though lone pair repulsions are there, along with that, this bond pair repulsions also plays important role. That's why because of these bond pair repulsions, for minimizing the repulsions, these two come closer or moves apart. Definitely they move apart, and thereby what happened to bond angle increases. That means if you compare bond angles between these two, then we are getting x greater than y. That means the magnitude of bond pair repulsions depends upon the electronegativity difference between central atom and the bonded atom. That's why in H2 and OF2, H2O bond angle is more than OF2. Now let us move to one more example. Now I am considering OF2 and Cl2O. Here also same central atom and same number of lone pairs near central atom. Here fluorine is more electronegative. Here oxygen is more electronegative than chlorine. Then definitely if you compare bond angles between these two, because bond pairs are very close to each other in the case of Cl2O, here x is less than y. But if you observe this Cl2O bond angle, it is more than tetrahedral bond angle. Normally, if you observe here in Cl2O molecule, fluorine is small size, chlorine is big size atom, and chlorine contains lone pairs, 3 lone pairs. Then fluorine also contains lone pairs, but fluorine is relatively small size, compact size. So because of big size, just now I concluded that between bond pair repulsions, because of more electronegativity of oxygen. In addition to that, in Cl2O molecule, because of large size chlorine atom, between these two also some repulsions takes place. Steric crowding we call it as. That's why bond pair repulsions plus repulsions between these large size bonded atoms. Because of this, here we have more bond angle. More bond angle means more than 109 degrees they observed in the case of Cl2O molecule due to two types of domination of repulsions. One is bond pair repulsions because of more electronegativity of oxygen. Another one is the steric effect of chlorine and chlorine. Now, one more example I am giving here. NH3, PH3, ASH3. That means I am giving here hydrides of 50A group elements, nitrogen family hydrides. Near each central atom, we have lone pair of electrons. Now, among these three, which one has more bond angle? That means if you move from arsenic to phosphorus or phosphorus to nitrogen, definitely in the case of nitrogen, we have more electronegative central atom. If we have more electronegative central atom in ammonia molecule, the bond pairs are close to each other, and between these two, between these bond pairs of electrons, more repulsions takes place. Because of more repulsions, definitely bond angle what happened here increases. That means in these hydrides from nitrogen to phosphorus, phosphorus to arsenic, as electronegativity decreases, definitely this compound has more bond angle. That means top to bottom the bond angles decreases. This same concept we are applying in 6th group hydrides also. I am taking H2O, next I am writing here H2S. Like that we have hydrides of 6th group elements, 2 lone pairs are there. This oxygen is more electronegative. Because of more electronegative character, bond pairs come closer, therefore more bond angle in the case of H2O. So, here also bond angles gradually decreases. This is the significance of bond pair repulsions based on the electronegative difference between central atom and bonded atom. Now, let us move to next factor. Now, I am going to formaldehyde molecule HCHO. In this formaldehyde molecule, this is the structure of formaldehyde. Central atom carbon, sp2 hybridized carbon, and we have here X and Y I am writing. Now, I am comparing these two bond angles. So, if you observe the experimental values, this X value is less than 120 degrees and Y value is more than 120 degrees. That means these two bond angles are not equal. This one has more than 120, this one has less than 120, even the central atom is sp2 hybridized carbon. Why this abnormality observed in the case of formaldehyde molecule? So, in VSEPR theory, we have one conclusion, effect of multiple bonds on adjacent bonds. Triple bond influence is more on adjacent bonds, next double bond influence. That is why these two bonds influenced by this multiple bonding, and thereby because this multiple bonding effect, these two come closer. These two come closer means definitely bond angle decreases here and this bond angle increases. So, this is the influence of multiple bondings on bond angles. Now, let us move to another bond parameter, that is bond order. Bond order, just now we observed in molecular orbital theory, according to molecular orbital theory, according to MOD, bond order is equal to half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. This is one method of calculating bond order. And one more method I am giving here for molecules having resonance structures. If molecules or ions having resonating structures, then we can find out bond order. Bond order is equal to total number of bonds around the central atom by total number of atoms around the central atom. Total number of bonds around the central atom by total number of atoms around the central atom. For example, I am taking here CO3 2- ion. We call it as carbonate ion. In this carbonate ion, this is the structure of carbonate ion. Definitely, it has resonating structures by changing the pi electrons. Now, in this molecule, in the beginning also I told resonance influence bond length values. So, according to this resonating structure of carbonate ion, bond order is equal to number of bonds around the central atom, that is 4, by total number of atoms around the central atom, that is 3. That means bond order becomes 1.33. So, this 1.33 fractional bond order also indicates the bonds are intermediate between single bond as well as double bond. That is the influence of resonance and bond order. Suppose one more example I am giving here, NO3- nitrate ion. In this nitrate ion, nitrogen double bond O, nitrate ion, because nitrogen maximum covalency is 4. Then in this nitrate ion, bond order is equal to total number of bonds around central atom 4 by total number of atoms around central atom, that is here also bond order is equal to 1.33. So, like that, if a molecular ion having resonating structures, then for those resonating structures, bond order is equal to number of bonds around the central atom by number of atoms around the central atom. But we have one more problem, resonating cyclic structures in some cases we have. So, in the case of resonating cyclic structures, this formula is not suitable. So, in case of cyclic structure having resonating structures, bond order is equal to one more expression I am giving now. Now, for cyclic compounds containing resonating structures, bond order is equal to total number of bonds in the ring by total number of atoms in the ring. For example, I am going to benzene. One of the resonating structure of benzene, we have hydrogens also. Carbon hydrogen no problem, because carbon hydrogen all are single bonds only. So, if you have carbon hydrogen bond order is 1, but now I am asking here carbon carbon bond order. In benzene molecule, carbon carbon bond order is equal to total number of bonds in the ring, means 9, by total number of atoms in the ring, that is 6. That means bond order is equal to 1.9. So, this bond order is equal to 1.9 also indicates in benzene carbon carbon bond lengths are not equal to single bond length, not equal to double bond length, but that carbon carbon bond length always intermediate between single bond and double bond. We all know carbon carbon single bond length is 1.54 angstroms and carbon carbon double bond length is 1.33 angstroms. This is C single bond C, this is C double bond C. But in the case of benzene, the carbon carbon bond length is 1.39 angstroms. So, not average, intermediate between these two. That means in benzene molecule, all carbon carbon bonds are equivalent due to resonance, and according to bond order, the carbon carbon bond order is 1.5. This fractional bond order also indicates in benzene the carbon carbon bond length is not equal to single bond and double bond length, and we are getting intermediate value. So, this is about bond order. ఇప్పుడు మనం కొన్ని క్వశ్చన్స్ ప్రాక్టీస్ చేద్దాం ఈ కెమికల్ బాండింగ్ చాప్టర్ మీద. ఫస్ట్ క్వశ్చన్, విచ్ ఆఫ్ ద ఫాలోయింగ్ వుడ్ హ్యావ్ ఏ పర్మనెంట్ డైపోల్ మూమెంట్. ఇక్కడ 4 స్ట్రక్చర్స్ ఇచ్చాం, ఈ 4గిట్లలో దేనికి డైపోల్ మొమెంట్ వాల్యూ ఉంటుంది, పర్మనెంట్ డైపోల్ మొమెంట్ వాల్యూ. నౌ ఫస్ట్ ఆప్షన్ SiF4, central atom is silicon. The silicon contains 4 valence electrons, carbon family, 4 fluorines are there. That means we are getting 4 electron pairs, all are bond pairs. If we have 4 bond pairs, then structure of the molecule is tetrahedral. So the first compound has tetrahedral symmetry. Because of tetrahedral symmetry, the resultant dipole moment becomes equal to 0. So this compound, ఈ కాంపౌండ్ కనుక మనం చూసుకున్నట్లయితే దానికి పర్మనెంట్ డైపోల్ మొమెంట్ ఉండదు, 0 డైపోల్ మొమెంట్ ఉంటుంది. నెక్స్ట్ థర్డ్ ఆప్షన్కి వెళ్తాను నేను, XeF4. In XeF4, xenon central atom which contains 8 valence electrons, 4 fluorines are there. That means we are getting 4 bond pairs and we are getting 2 lone pairs also. So if we have lone pairs, immediately you are expecting some distortion in the shape, but even though lone pairs are there, so totally 6 electron pairs are available. If we have 6 electron pairs, the electron pair structure is octahedral. In that electron pair structure, according to VSEPR theory, we have to accommodate 2 lone pairs. The first lone pair in a position, but the position of second lone pair is opposite to position of first lone pair. Suppose I am writing one lone pair here, second lone pair opposite. So this is electron pair structure is octahedral, but the molecular structure becomes square planar. That means the influence of lone pair here cancel out. That's why this molecule, even though lone pairs are there, for this molecule dipole moment becomes equal to 0. Now if you observe BF3 molecule, boron central atom, it contains 3 valence electrons, 3 fluorines are available. So totally we got 3 electron pairs, all are bond pairs. If all are bond pairs, then this molecule becomes trigonal planar structure. Because of trigonal planar structure, definitely the bond moments cancel out and resultant dipole moment becomes equal to 0. But if you observe SF4 molecule, sulfur contains 6 electrons, 4 fluorines are there. So out of 6 electrons, 4 electrons involved in bonding with 4 fluorine atoms, and thereby we are getting 4 bond pairs. So sulfur 6 electrons are available and 4 fluorines, and this is lone pair. So overall bond pairs 4, lone pairs 1, means totally we have 5 electron pairs. In 5 electron pairs, the electron pair structure is trigonal bipyramidal, but according to VSEPR theory, in trigonal bipyramidal structure, lone pair occupies equatorial position, and thereby this molecule is not symmetrical molecule, and this molecule is called as distorted tetrahedral or seesaw structure or folded square type. That's why for SF4, resultant is not equal to 0 due to unsymmetrical structure. That's why correct one is SF4 molecule, because I am asking which of the following will have a permanent dipole moment. That means SF4. Now let us move to second question. Which of the following arrangements of molecules is correct on the basis of their dipole moments? So this dipole moment once again depends upon the structure, depends upon the lone pairs and bond pairs also. Normally symmetrical molecules have 0 dipole moment. The total 3 molecules are given. Out of 3 molecules, if you observe BF3, that BF3 it has symmetrical molecule trigonal planar structure. That's why for BF3 dipole moment equal to 0. Now we have to compare the dipole moment values between ammonia and NF3. So BF3 0 dipole moment. So NF3 and NH3 lone pair. So here nitrogen, fluorine, fluorine is more electronegative, fluorine is more electronegative, fluorine is more electronegative. And this is for these three resultant in this direction. But lone pair is there, this lone pair is always away from the central atom. Now, if you observe resultant of these two and lone pair moments, both are somewhat cancel out. Not 0, but definitely some value it has. But in the case of ammonia, nitrogen is more electronegative, nitrogen is more electronegative, nitrogen is more electronegative. Here, for these three resulted in this direction. So now both are in the same direction, then resultant value becomes more. So here bond pair bond moments and the lone pair moments are in the same direction, whereas here in NF3 molecule bond pair moments and the lone pair moments are in the opposite direction. That's why resultant becomes less, even though fluorine is available, even though more electric fluorine is available. Among these two, NH3 has more dipole moments. So least one is BF3 and highest one is ammonia molecule. So ammonia greater than NF3, greater than BF3. This is the correct option. Now let us move to one more question here. Three species are given: ICl2 plus, ICl2 minus and ICl4 minus. Some of the bond pairs and lone pairs and each iodine atom are respectively I am asking. So first I am writing ICl2 plus, iodine central atom, 7 electrons are there and 2 chlorines are available, means 2 bond pairs, 1 electron I am removing because of positive charge. Now we have 2 lone pairs, total means 4 electron pairs in ICl2 plus. Next coming to ICl2 minus. So iodine central atom, that iodine contains 7 valence electrons, 1 more electron I am adding due to negative charge, 2 chlorines are there, that means 2 bond pairs are available and 3 lone pairs are available. So total electron pairs 5. So in ICl2 plus total 4, in ICl2 minus total 5. Now let us move to ICl4 minus, iodine central atom, 4 chlorine atoms are available. So 1, 2, 3, 4 and negative charge is there, 1 more extra electron, that means 2 lone pairs and 4 bond pairs. Total electron pairs in ICl4 minus is 6, because I am asking here sum of the bond pairs and lone pairs and each iodine atom are respectively. So 4 electron pairs, 5 electron pairs and 6 electron pairs. That is why the correct option is 4th one.